Welcome to lecture 10, and we will continue with our derivations for different strains. And yesterday we worked out the formula for longitudinal strain, isn't it? And we found out that longitudinal strain epsilon depends on the location, which is the reference location x here, as well as the direction of the line element that we are looking at. And it turned out to be square root of f transpose f into n dot with n minus 1, right? Where n is again the direction of the line element in the reference configuration. To denote that it's in the reference configuration, what we are going to do is we'll put a subscript naught here. Okay, so n naught with a naught means it's the direction of line element in the reference configuration. If it is without a naught, then it's the direction of line element in the current configuration. Okay, that's the language that the book is following. And of course, you also saw that the stretch lambda square, for example, was simply f transpose f n naught dot with n naught, and you had seen that this was same as f n naught dot with f n naught, right? Which you could also write as f n naught magnitude whole square. So lambda is simply magnitude of f n naught. Okay. And if I asked you what is the current orientation of the line element, then what would you say? What is n, for example, of the line element? Which is to say the current direction of the line element. So you can see it is without a naught. So anybody, can you tell me what is the current direction of the line element? This is an easier question, of course. And I'm talking of infinitesimal line element. So you already know the transformation. dy is equal to big F dx dy by mod of dy. Yes, that's true. But what will that come out to be? When you're right that this is dy by mod of dy. In terms of big F and in terms of the orientation of the element, undeformed orientation, what is that going to come out to be? You see, this f dx is also equal to um, mod of dx into big F n naught. Can you see that? Because dx itself is n naught times mod of dx. right? And mod of dx being a scalar, I just took it out. Like I told you, I can take this scalar out. And with this representation for dy, what do you think would be the current direction? Can we say that it is same as divided by mod of this thing, right? Okay, so you know the deformed length, or how much is the stretch in a line element, and how the orientation has changed of the line element. All that you can find out from the information of deformation gradient, isn't it? Even in the strain formula, see the deformation gradient is present there. You have to tell just the orientation of the undeformed line element. Okay, so that is about strain orientation. Sorry, the longitudinal strain. Then, of course, you also know about what is called shear strain, which is to denote the change in angle. So let us try to find out that formula also. Okay, we'll work out all the formulas and then show how we can approximate them to the undergraduate formulas. Okay, but today let us just work out all the formulas. So the next is about change in angle. So to measure change in angle, you of course need two line elements. Just one line element is not sufficient because you are measuring angle between line elements. No? You need to have two line elements. So again, think of the reference and deformed configuration. And here we will start with infinitesimal line elements only, because we have seen our exercise of delta x limit tending to 0. Why was that needed? That was to get the local value of strain. So having seen that, we are now going to limit ourselves to infinitesimal line elements. Okay, so we are at a point, let us say x, and think of two line elements. One is dx1, and then you have dx2. Okay, and the angle between the two line elements need not be 90 degree, it can be arbitrary. Okay, so let us say this angle is theta naught, right, because it's the initial angle. So finally x goes to y, and the two infinitesimal line elements, that's why I'm denoting them by d and not by delta. Okay, so they may have become like this. So this is, of course, it's a zoomed view, dy1, and this is dy2. And we know that dy I, for example, is equal to big F into dxi, right? So, and we want to know this angle here, theta. What is the final angle? So, any idea how to do that? Anyone? How to obtain the final angle? What should be the way forward? dot product for final ns dot product. That's right. So why don't we take the dot product? It will give you cosine of the angle, right? So cosine of that angle theta is then dot product dy1 dot dy2 and divide by the magnitudes of the two line elements, right? Okay, and this we can now use the formula relating undeformed and deformed line elements, and what we get is big F dx1 dot big F dx2 divided by, okay, so in the denominator we have dy. Can't we write it as lambda 1, right? Lambda 1 into magnitude of dx1 and the other one is then lambda 2 into magnitude of dx2, isn't it? And then you know what to do. This being a scalar, I can move it wherever I want. So why don't I take it and move it here? And likewise for this one, I move it here with the vector dx. But in the denominator, so it has to be divided. And when you divide it, then what do you get? That direction, right? So very good. So it's f n naught 1, isn't it? Dot with f. See, I'm putting a lot of distance to ensure that you have to first get the vector f into n naught and then has to be dotted. Divided by, and of course the bottom thing is easy, lambda 1 into lambda 2. So I just write it as lambda 1 lambda 2. So that's how you get the angle between the two line elements. I mean, it's cosine, so to get theta, simply take cos inverse, and theta minus theta naught minus theta will give you the change in angle from the reference, right? I mean, that's the theta naught minus theta is then by how much that angle has shrunk, and which is a measure of shear, isn't it? That's how we used to denote the shear, no? So theta naught minus theta, that's the measure of shear. So this was quite easy because we did the exercise yesterday. But you will see that it looks quite different, right, than what we have learned in our undergraduate. Also, this big F right now is quite abstract. The undergraduate formula for shear is, for example, this gamma 1 2 is del u1 by del x2 plus del u2 by del x1. Remember? So it is in terms of the derivatives of displacement. So when we work out, this formula or the ones that we derived earlier in terms of displacement, the big F has to be written in terms of displacement, and then we'll do approximation to show that indeed it reduces to the undergraduate formula. Okay, so that's about the shear. We got it very easily. What's the next thing that we can look at? Also notice that this formula depends on both n01 and n02. It is of course dependent on the point x, but also on the two directions of the line element that you chose. So at a point, just like you have so many longitudinal strains depending on which line element you have chosen, similarly at a point you have so many shear strains depending on which two line elements you chose at that point. Okay, so there is no unique value for shear strain at a point. It all depends on which two line elements you have chosen. Okay, and I hope you have appreciated this in your undergraduate class also. If not, then you should really appreciate it now that you have infinite values for shear strains at a point. So having derived this, let us try to relate the volume. So again, you have this body here and the deformed body. So how is a small volume here, the volume of a small region here, what happens to this volume when it gets deformed and let us say it becomes like this? So let us say the volume here is V naught, or I should say dV naught because it's infinitesimal volume, dV naught, and here it is dV. Okay, so what's the ratio of these two? That's the question. Okay, and you can take this small volume anywhere in the body. So it could be, for example, here, and this may have deformed like this. So the next question that we want to tackle is how do we relate the two volume elements? You see, it's called volume element. We started with line element, then we had two line elements, and now we have volume element. Okay, so anybody having idea how to do this? So to pick a volume element, you can take the help of three line elements which could form the sides of parallelepiped. Okay, let me show you here. So think of a point X and a parallelepiped. Okay, so and here is that point X, and you have three line elements. This is say dx1. This one is dx2. Okay, and the other one, which is the dotted one right here, that's dx3. Again, it's a zoomed view. Okay, it's a zoomed view, but it's an infinitesimal parallelepiped. Okay, because the sides are so small, no? Of zero length actually. So this parallelepiped is actually at the point x itself. It's just looking big, and once it gets deformed, then it may have become like this. Okay, where this one is, of course, this is y. This is dy1. This is dy2, and then you know where is dy3, right? So now what's the volume of a parallelepiped? If you know the three sides, what's the volume of a parallelepiped? Anyone? Cross product, box product. Okay, I never heard this name box product, but it looks a very nice name. I understand what you mean. STP, what is STP? Oh yeah, scalar triple product, of course. That's what one says. That's right. So it is a scalar triple product. And Anas says 1 by 3 into area into height. That's for what is called cone, no? It's for a cone, not for a parallelepiped. But it's basically a scalar triple product, okay? So you can take, for example, dx1 cross product dx2. And do you know what does cross product give you? So if you take these two sides, then the cross product is going to give you, look at this. So cross product is a vector which is directed along the normal to that face and whose magnitude is same as the area of that face. Okay, so I can write it as blue face area. So it gives you the area vector of that blue face. And then you have to dot it with, so once you have the base area, multiply with the height of the parallelepiped. And to get the height, you have to drop a perpendicular bisector, or you have to draw a perpendicular line from the other vertex, and therefore you dot it with dx3. Okay, that's how you get the scalar triple product. So this is actually the volume dv naught of the parallelepiped. Okay, so if you know this volume, then you would also know the deformed volume then, right? So the deformed volume dV is simply dx or dy, because sides are now y's. dy1 cross product dy2 and then dot with dy3. And of course you also know that you can have the cyclic permutation also, right? For example, this is same as dx1 dot with dx2 cross product dx3, isn't it? It's now a different phase multiplied by the height. And then there is third one also, right? So that's the beauty of the scalar triple product. And each of the triple products have a physical sense, isn't it? Anyway, so this is how you got the formula of the two volumes. And now we want to write down dV in terms of dV naught. So obviously you have to now use that transformation. So you can say that dV is then big F dx1 cross product big F dx2, okay, dot with big F dx3. All right. So anybody having idea what could be the next step? We need to define X now so that we can create a skew symmetric matrix. Okay. But why would you? Okay, you want to convert this cross product into a skew symmetric thing. Well, I'm not sure if that will help. But how many of you know that you can realize a scalar triple product as the determinant of a matrix? Anybody has realized that? So A dot B cross C, for example, A dot, let us say A cross B dot C, which is same as, of course, A dot B cross C, can be realized as the determinant of a matrix so the way to do that is, think of a matrix whose columns are A, B, and C. So the first column, form it from A, okay? Second column, form it from B. Third column, form it from C. And here you have this matrix. And determinant of this matrix is same as A cross B dot C. Okay. This you can also prove using what is called index notation. Because for the determinant of a matrix, there is a formula, index formula, which you have already seen from my classes, and show that it is equal to what you get from the scalar triple product. Okay. So having seen this viewpoint, then dV We can write it as determinant of a matrix formed by those three vectors. First one being big F dx1, right? The second one being big F dx2, and the third one being big F dx3. Okay? And this matrix that you have here, you could also write this matrix as the matrix big F multiplied by this thing over here. Do you agree with me? See, when you multiply these two matrices, you will exactly get what you have here. First matrix, see, you have two matrices here, right? This into this. Work out the multiplication. First matrix into first column is giving you this thing over here. So these two when multiplied, well, let me use another color. So when you multiply first matrix into first column, that gives you the first column of the resultant matrix. Then again the first matrix into second column, that gives you second column of the resultant matrix. And likewise for first matrix into third column. Are you guys with me? It is not so easy to see this. So think of two matrices, okay? A and B. And the product is C. Then what is Cij? Isn't that Aik into Bkj? Right? And there's a summation over K, of course. Anybody not comfortable with this? Cij equal to Aik into Bkj? So let me now try to get using this formula, let me try to get the first column of C matrix. So first column would mean J has to be equal to 1 then, right? J has to be equal to 1. So Ci1 is then Aik into Bk1. Okay? And if I want to write this for each of the i's, I equal to 1 to 3, so that I really get the full column of C. C11, C21, C31. So that's the first column of C. So I have written this for each of the i's. So what do you get then on the right hand side? Well, before that, also see that this Aik into Bkj is like you take the ith row of A, so that's AI1, AI2, AI3, and multiply with jth column of B1j, B2j, B3j. Isn't it? Take the ith row of A and multiply with jth column of B. That gives you Cij. So if that is the case, and I want C11, what will be C11? Take the first row of A and multiply with first column of B. C11 is take first row of A then C21 is the second row of A, right? Multiply with the first column of B. So each time you have the same B. Similarly, C31 is third row of A and multiply with the first column of B. But you see this whole thing finally is giving you first column of C. This is same as the full A matrix. You see, this is the full A matrix multiplied with the first column of B. And this is what I was telling you here. If you want to get the first column of the resultant matrix, then you multiply the matrix times the first column of the second matrix. Okay? So I hope with this little detour, you are able to understand this decomposition. Anybody not able to follow? Okay, so having seen this, we can now proceed further. Can we now write that dV is therefore same as, you see, determinant of, you have two matrices here. It's the same as the determinant of product of two matrices is same as product of determinant of the two matrices. That's the determinant rule. So that means it's same as determinant of F multiplied with the other one, determinant of this dx1, dx2, and dx3, isn't it? But again, this number is scalar triple product, right? And or same as the original volume. It's in terms of dx. So that tells me that dv is equal to determinant of f multiplied with dv naught. Okay, so ratio of the volume is simply dv by dv naught. That's equal to det f. Okay, this is how we derive this formula. Any questions so far? Can anyone tell me what is the peculiarity about this relationship that we got and the other two that we derived earlier, the change in angle or the longitudinal strain. So Mahadevana is asking, is X a corner of infinitesimal cubic unit or centroid of cube? So in our current construction, X was at the corner. X is at the corner and then the three sides are emanating from it. Okay. Yeah, so tell me what is peculiar about this formula? Anybody? It certainly is quite simple than the earlier two, no? Why is it simple? No direction. Very good. You can see the three line elements directions are not coming here. And not 1 and not 2 or and not 3 is not showing up here. What does it mean? Yes. Independent of position. Well, no. This big F depends on X, no? It is independent of direction, yes. So it is independent of the direction of line elements. So very good. So what this tells us is that the ratio of volume, it is independent of directions of the line element that you choose. This also means that it is unique at a point. So therefore it is unique at a point. So once you get this volumetric, this ratio, the volumetric strain is simply -1, right? So volumetric strain is therefore, it is unique at a point. There are infinite longitudinal strains at a point, infinite shear strains at a point, but unique volumetric strain at a point. Okay. All right. So we saw the how the length is changing, how the angle between elements is changing, how the volume is changing. What more do you think we can track? Yes. Anything else that we can track? Okay, so there is some question, sir. If we take any other type of infinitesimal shape, so that's also a very good question. So we started with a parallelopiped. What if we had taken some other shape, some arbitrary shape of the volume? So it turns out that it is independent of the shape of the volume also. But the proof is, of course, not so easy, that proof. Okay, but it is independent of the shape of the volume also. Okay, so we saw length change, volume change. Maybe we should also look at how the area is changing, right? So that's the next thing we want to look at. Change of area. So again, we have our favorite picture, and we are at a point X. To get area, we would need two line elements, okay? So this is your dx1, that's your dx2, and the cross product of these two is the area formed by the parallelogram here. Okay, so you can construct area by just taking the cross product of two line elements. Okay, the parallelogram is the magnitude of the area, and the normal to the parallelogram is your normal to the area. So basically you can write, let us say, dA naught as dx1 cross product dx2, and dA naught is the area vector, by the way, which you could also write it as n dA naught. Okay, where n is the surface normal, by the way. N is the surface normal. So I want to see what happens to this area in the deformed configuration. So it may have become like this, right? So that means dA is dy1 cross product dy2, which is, okay, I need n naught here, by the way, is same as n dA. So can we write dA in terms of dA naught? That is the question. So of course we move ahead by replacing dy with f dx, right? So this is same as f dx1 cross product f dx2. What should we do the next thing? Are the lines remaining straight in a deformed configuration, or are we assuming? So you remember that it's a zoomed picture, but they are infinitesimal line elements. Okay, so they of course remain straight once they deform. That is something we have seen in the beginning. So dy and dx, they are both straight. They are infinitesimal line elements. Okay, any idea how to move ahead? It's of course the area vector. So what we can do is, why don't we dot it with f dx3, just like earlier. So dA dot f dx3, that's equal to f dx1 cross product f dx2, and that's dotted with f dx3. And this we just found out this is same as det f into dx1 cross product dx2 dot with dx3, right? But this thing over here, I'll write it as, you see what do we have here? dA is a vector, so dA is a vector, it is dotted with a tensor times dx. So if I bring this tensor on the other side, what is going to happen? That's going to become transpose, no? So I could write it as F transpose dA dot with dx3, that's equal to det F into dx1 cross product dx2 dot with dx3, right? But also understand that here, suppose I have fixed 1 and 2, the third one can be arbitrary, right? Given 1 and 2, you can choose third to be anything, dx3. So this is like an arbitrary vector, an arbitrary vector. So basically, if you have an identity A dot B equal to C dot B for any B, if it holds for any B, for all B, then you can show that A is equal to C, isn't it? Because it holds for all B, not for a particular B. So using this, we can derive that F transpose dA is then equal to det F of dx1 cross product dx2. Okay, but then this thing inside the bracket is the original area. So that means, and it, okay, let's go one by one. F transpose dA, that's equal to det F into dA naught. Okay, or the deformed area is, then you bring this F transpose on the other side, what you have to do is take the inverse, right? So that's det F, it's a scalar, into F inverse transpose into dA naught. So that's the relationship for the area. So this is how area elements transform. And it also has a name, it's called Nancy formula. Okay, Mahadevana, it's a very nice name. It's matrix vector multiplication. You are saying what will be the significance of eigenvalues and eigenvectors of F? So that will come to later on. Okay, it has a lot of significance. So there were several new things today. So I'm sure you may be having some difficulty in catching up. but please just brush it up, or what I mean is look at it again slowly. You will understand it. Yeah, tell me.
Sir, in change in area, you write dA naught equals to vector dA naught and dA equals to and vector dA. You write surface normal same to both. Is it same, sir?
Where do you mean? Where have you written that? dA
Sir,
equal
in
to?
change in area. Sir,
Yeah, where?
in change in area, dA naught equals to and surface normal into dA naught.
You mean this dA naught is equal to n naught into dA naught?
Sir, both dA naught and dA you write in terms of surface normal and naught. So n naught surface normal will be different or same.
See, this n naught is the surface normal. It is not the direction of line element. So very good question. This is not the direction of line element here. It's a surface normal, which is so, or you can say this n naught is then defined as dx1 cross product dx2 divided by magnitude of it. It's not the direction of line element.
Okay, sir.
Yeah. So if not, then let's say goodbye for today, and see you guys on Friday. Of course, today also 8. I'll be there at 7:50. See you then. Bye bye.